Okay, so let's start. Okay, so first of all, I'm sure that each one of you has started to do the exercises, and I'm also sure that many of you have recognized the first mistake, the first typo in exercise 2, where the components of this matrix clearly were not properly defined. So I really encourage you to try the exercises to let me know the mistakes. They're not intentionally placed everywhere, but they are everywhere. So in particular, if you have to take the exam, the fact that you recognize typos and come to me and tell me will be highly, highly considered. Okay, so yesterday we were discussing the spectral properties of random matrices. And okay, which I'm very happy somehow are finding a nice relation with the lecture on random circuits. So let's sum up what we discussed about the eigenvalue properties of random matrices and why somehow we spent so much time on them. Now, namely, the important point is that it has been recognized that the eigenvalues now of generic Hamiltonians, generic local Hamiltonians, share the same statistical properties of the random matrices that we were discussing yesterday. And this is true from several point of views, so from the point of view of the level spacing, from the point of view of the spectrum form factor, and other quantifiers at the level of the eigenvalues. Now, this kind of finding was established, so it has a long history and we're not going to talk about it, but let's say that in the classical limit, so in the case in which we have a classical limit that we quantize, so we can think in the limit of small h bar, this was established in the famous Bohigas-Giannoni-Schmidt conjecture, which allows somehow to interpret this kind of results and to really elevate this from the semi-classical case to the purely many-body case, so h bar equal 1. This has been one of the great achievements of these kind of toy models of chaos with random circuits, with, let's say, with local circuits. And this is why there is this nice correspondence with the other class. So this is for random generic Hamiltonians, so this nickname for quantum chaos, these Hamiltonians which we cannot solve, where we do not have symmetries. Now, the other important fact is that what was somehow recognized is that instead the eigenvalues of integrable systems or localized systems have the same properties of independent random variables, which instead show, say, Poisson distribution. Yes? Sorry, can you repeat? Okay, in proper dimensions. So of course it has to be, okay, that's a good question. So we always have to consider h bar. When we mean the limit of h bar to 0, what we mean is that we have enough, so h bar can be seen as a way to define the level spacing, so how many eigenvalues we have. And when we say h bar is going to 0, so what we consider is that we have enough energy eigenvalues such that the spacing is effectively going to 0. And now it's really important that somehow we send h bar to 0 in the appropriate way, such that we still have many eigenvalues. And we're going to say something like this also in the many-body case and make an analogy to this. Okay. But now what actually is going to be the rest of my lectures and also the point of today's lecture is the properties of eigenvectors. So the plan for today is in the first hour to discuss eigenvectors of rotational invariant random matrices, which even if they are completely structureless and somehow a bit disappointing, provide a good toy model for ETH. And then in the second part of the class, we are finally going to address this mysterious eigenstate thermalization hypothesis. Okay, so let's start from eigenvectors of rotationally invariant random matrices, which again we defined as those matrices whose probability distribution is invariant under rotations, okay? And I'm going to think about the situation in which U is a unitary. Okay, so what we discussed is that its eigenvectors are structureless, so I can imagine its components. So these are vectors like this, and okay, let me use Dirac notation. I can represent it in a given basis, okay? So these components C alpha I are nothing but the overlap of my eigenvector I with a generic basis. And now, as we saw in the previous class, these are somehow isotropically distributed. Which is another way to say that they're structureless. Okay. So since they're so, let's say, generic and structureless, so one can think about the let's say the minimal requirements on this kind of eigenvectors, okay, which are normalization, okay, and orthogonality. And besides these kind of two simple requirements, I do not want to put any other information. Okay, so let's go here. Now, so I did want to discuss a bit better this normalization issue, but I realized that maybe yesterday I was too fast. So I did cut a bit on the kind of content of the lecture, but I would be happy to discuss this a bit better. But let's just say that this kind of normalization, the only thing that is asking is saying that, that the distribution of the components, so I indicate it with the vector like this, okay? I'm just saying that this should be proportional to a delta function. Okay, some normalization. And here I'm considering the unitary case, okay, where these can be complex numbers. Okay, now from this simple requirement of normalization, what one can derive is the probability distribution of a single component. Namely, let me define y equal, let's say, I fixed I, and then modulo square. I can find the probability distribution of a single component. Yes? I would say yes, because in this case, so for this kind of rotational invariant random matrices, there is not really a meaning of, so there is no special ordering. None of them has, so I'm thinking if I'm saying something correct or not. But what I would say is that there is no structure, so every eigenvector is as important as any other. So you can always take an eigenvector which is not in the center of the spectrum and put it, so rotate it and put it in the center of the spectrum. This will not change its statistical properties. I think this is correct, but okay. So one can find the probability distribution for this y. And actually now, in the limit going d of larger matrices, d going to infinity, this kind of this probability distribution acquires a very special form. Okay, so let me actually write it like this. I write it for another variable, which is not y, but is y divided by its average. Okay, so this in the limit t going to infinity becomes a simple Poissonian. So this is known as the Porter-Thomas distribution. Okay, which is the probability distribution of a single component, of the normalized version of a single component. Now, I'm not going to do the derivation, but you can do it as an exercise, or it's hidden somewhere in the notes. But what I wanted to point out is that this kind of property of single components has a long history. So it's one also. It's a very old finding, and right now has several applications in different branches of quantum information. But what is nice is that in order to derive it, and I invite you to do it, you have to really just to impose the normalization of these eigenvectors. Okay, so it's kind of minimal condition to find this Porter-Thomas. Okay. But really, what matters to me is not this normalization, but is rather, I mean, what I would say the orthogonality, which fixes a bit more this kind of property of being isotropically distributed or structureless. So, okay, we have this CI/CJ, and the idea now that what we want is that we want these vectors to be normalized, okay? So we want two eigenvectors to be normalized. So we want basically to be equal to 1. So what this means is that this matrix of these overlaps, this actually defines a matrix U alpha I. So what I'm requiring is that these U, they're unitary matrices, no? So this is the only requirement that we ask from these matrices. And as we nicely saw in the previous lecture, besides that, let's say I do not ask anything else, so I'm going to consider a uniform sampling over the unitary group, which is the Haar ensemble. Okay. Now, the nice property, so the Haar ensemble has a series of very nice properties, and one of them that is quite useful is that the statistical properties of the matrix elements are exactly known. So, yes? Of the Hamiltonian H. Mm-hmm. Yes, sorry. Yes, sorry. Yeah. I first wanted to do, yeah, okay. So these matrix elements are exactly known, and this goes either under the name, of Weingarten calculus, okay, which is heavily used now also in the field of random circuits. And let's say, I would say that the explicit expression to compute these moments were given, okay, I like this kind of, these papers, but. So, okay, let's write down a bit of these matrix elements. And this kind of matrix, the statistics of this matrix element is known with an exact expression for every product of U's. So let's say the first property we have already written it. So u, let's say alpha I, and then u dagger beta j, or no, let me do this, alpha prime I prime on average. So here we saw there, somehow we want a delta function. And so since this matrix can be complex, the only way I can have something which is order 1 is that I couple alpha with alpha and I with I prime. So alpha with alpha prime and I with I prime. So this is I prime, alpha prime divided by d. Okay. So only indices that appear twice persist. This is kind of the idea. And this can be generalized also at higher orders. So let's write only the one at order 2. For instance, if you have I alpha, j beta, u dagger alpha prime I prime, u dagger beta prime j prime. This on average also is known. And now here that I have the product of 4 of them, I have to consider all the possible couplings, let's say of I with I prime or j prime, or with alpha prime, beta prime. Okay. So basically I have to consider all the possible permutations of the indices ij with I prime j prime, and of the alpha beta with alpha prime beta prime. Now, without going into the permutation studies, let me give you what is, for instance, the result in this case. You have delta I prime, delta alpha prime, delta j prime, delta beta prime. Then you have delta, now you couple this with this, okay? So you have delta I j prime, delta alpha beta prime, delta j I prime, delta beta alpha prime. Okay. And this somehow, so let me make a point, this somehow would be the result if these matrices were Gaussian matrices. So these, they're just the Wick contractions, no? So I'm coupling, basically I'm considering all the possible contractions of matrices in couples at this point, okay? So this one corresponds to the second term, and the first one we did was, let's say, this one, no? Okay, it's clear what I'm doing. But now, the important thing is that the Haar ensemble, so this kind of averages, this Weingarten calculus, goes beyond the Gaussian approximation. So one can also have other kind of contributions. So these kind of contributions are such that, for instance, okay, so let me erase this. Are such that, for instance, I do couple I with j prime, but now I couple alpha with alpha prime. Okay. And now let me take another color. So what is left, I take j and I put it with I prime, and my beta now goes with, no, this is, and beta goes with beta prime, yes, thank you. Okay. So the fact that I'm considering something which is a bit weird comes with a price. So this kind of more complicated contribution is suppressed in 1 over d. So the kind of treatment, it's true that it's Gaussian in the large D. But I'm going to go back on this. So what did we write? This is delta I j prime, delta alpha prime, delta j I prime, delta beta prime, and then I have to do the converse, no? So I couple I couple it with I prime, but now alpha I couple it with B prime. So this is I prime, delta alpha, beta prime, delta J, J prime, delta beta, alpha prime. Okay? Oopla. Okay. So again, what we're saying here is that basically there is a leading contribution which comes with a given normalization, okay, which is hidden in the calculation. So at the leading order, it's Gaussian, and then there is a subleading correction, which is non-Gaussian. But this kind of subleading correction is important in order to assure the orthogonality of the eigenvectors. So it is not there by chance. Okay. And now, I mean, there is so this is for 1 and 2, and then there is, yes? Yeah, you can say this, so, yeah. So actually what you're doing, you have to sum over all possible permutations of the indices. So there is a closed expression in terms of all the permutation on the symmetric group when you consider 2K products of matrices. So the expression is in the notes, but okay, it's useless if I rewrite it here. And it involves all permutations of the indices and then a matrix. So you see here there are some numbers. It's 1 over d squared minus 1, 1 over d with a minus, okay. So there is a matrix which is called the Weingarten matrix, which tells you which coefficients you have to put, and this is beautiful combinatorial interpretations, okay. We don't want to go in all this, but it's actually very interesting and useful to compute a lot of things. Now, what I want to do instead is, let's say, to use this kind of Weingarten calculus. Again, let me reiterate, we are considering the unitary case. So the Weingarten is defined for unitary matrices, for products of unitary matrices. Okay. I want to use this kind of expectation values now to give you a sort of toy model of ETH. Okay. So I want to see how the statistical properties of eigenvectors are reflected in the statistical properties of matrices in a random basis. So what I'm calling toy model of ETH. Of course, you still don't know what is ETH, so this is going to be clear later, okay? Now, the only thing I want to say is when I want to see how, let's say, isotropically distributed vectors have an impact if I look at the statistical properties of ij, where ij is the expectation value of a given matrix in a random basis. So I take a matrix diagonal, okay, or let's say a given matrix A. Okay. And I want to look at its matrix elements in a random basis. So sum over alpha, A alpha, and then I have how did I write it? Okay, I realized that this is the opposite of what I wrote here, but no, so this is, thank you, it's not, this is for every D. We will be, yes. Because you see in the limit of large D, so maybe there is a big open parenthesis in front of this is in front of everything, and then there is a minus 1 over D. So this is small, so you would be tempted, and okay, this is fair, to say this is Gaussian, this is a Gaussian vector, but actually it's not Gaussian. So there are this kind of subleading contribution. But now I'm going to show you why we like these subleading contributions, and that there are often cases in which we do want to keep them, and they have an impact, okay, in this kind of toy model. Okay. So now what I want to do is, let's say I want to compute the statistical properties of this Aij. So let's start doing this exercise. So I want to compute the statistical properties of this Aij. And now, before doing the exercise, let me say, okay, let me make a sketch of this matrix, Aij. So now the fact that these are random, okay, I'm going to have that these matrix elements, they're going to be random, no? So if you do it on your computer, this matrix in general, it's going to be something like this. Okay, so you're going to have random phases all over this matrix without structure. So somehow this, I don't know, goes a bit, maybe in these, yeah, they have no structure, so each of them count the same way. Okay. So, okay, at this point, let me compute these statistical properties. So what I have to do, I simply have to compute these, A alpha, UI alpha, U alpha J dagger. And here I substitute this expression 1. Okay, so what is this? This is 1 over D. So I put the constant in front. Then I have delta ij, okay, and then delta alpha. So this becomes simply something like this, sum over alpha A alpha. Okay. So I find a result which depends only on the eigenvalues of alpha. What is this? So let me write it like this. This is delta ij alpha, the expectation value of A. Why? Because, so this is the trace of A, right? I'm summing over all its eigenvalues. So okay. So yes. I made an. I'm sure that you're right. I'm wrong. I don't see. What? Can you repeat? Where did I put beta? Ah, yeah, you're sure, yeah. No. No, for once. I didn't make. No? Yeah, I'm just saying I have a matrix. I can always diagonalize it, so I represent it in its diagonal. And then, so this is, now the point is that this kind of properties, okay, so here I'm writing it in its diagonal form. The important properties is that the statistics of R matrices, they're true in every basis. So now these, they hold independently of, let's say, the choice of alpha and beta. So if you want to redo it, let's say, do the exercise with a matrix which is not in its diagonal form. So you write it as A gamma, gamma prime, gamma, gamma prime, you're going to obtain the same at the end. So namely, what we wrote, okay, something maybe a bit trivial, we're saying that the average is finite only if I is equal to J, okay? And this somehow from the idea that, okay, you have all these which are random signs makes sense, so only I equal to J gives me a finite average, and then it depends only on the trace. So the fact that it depends on the trace, it depends on the invariance of the matrix, so on its eigenvalues. This, you remember, I said that yesterday there is a factorization between eigenvalues and eigenvector properties, no? For this kind of objects. So now, let's have, let's do the other exercise, which is to compute products. Okay. So now I want to do Aij, Aji. Okay. So this is sum, now alpha beta, and this is A alpha, A beta. ui alpha, u alpha j dagger, u j beta, u beta I dagger. Okay? Check if I'm making mistakes. And now I substitute the expression above. Okay? So let me do it for you. This is 1 over, so I put the constant, d square minus 1. Then I have to sum over alpha beta, a alpha, a beta. And then this, the expression above gives me a delta ij plus delta alpha beta. These are somehow the Gaussian contribution, minus 1 over d. And then delta ij, delta alpha beta, plus 1. Okay. This, okay, you have to check that this is true, okay, so you just put the indices. Okay, so let me massage this expression. So I take a 1 over d square in front, so this becomes 1 minus d to the minus 2. Very sophisticated math, okay? And now let's have a look at the various terms. So I rewrite the constant in front. Okay. So now the first term is not talking to alpha beta, so I get delta ij, and then basically I have sum over alpha of a alpha divided by d. This is the expectation value of a. And then I have sum over beta of a beta divided by 2. So this is a square. Okay, this is the first term. Now let's do the one with alpha equal to beta. It's clear what I'm doing? Okay. Now I'm doing the one alpha equal to beta. So here you have plus 1 over d square, sum over a alpha square. What is this? The average of a square. Okay, good. So here there is a 1 over d square. So I reabsorb 1 of the d, 1 I leave it here. So I get basically a square over d. Okay, now let's go on. Then here I have 2 of them. So I have delta ij, so let's write it. And then I have delta alpha beta. So this becomes alpha a square. Okay. And then I have a plus 1. So this gives me no deltas, and this is just a square divided by d. Okay. Now notice, now we are going to take the d going to infinity limit, but I want you to notice the following, these last 2 terms, which we kind of were tempted to neglect. So this non-Gaussianity that was here, it's coming here. Okay. But you see, this term here has exactly the same dependence with the dimensionality of this other one. Okay. So you kind of want to send d to infinity at the end. Okay. So now, with this in mind, let's rewrite the result in a nicer form. Okay. So what are we doing with this exercise? We are saying that a ij on average is equal to delta ij a. Okay. Then we are saying that now I send d to infinity. Okay. So what it means I send d to infinity, basically I neglect all terms which are ordered d to the minus 2. So specifically, what I mean is that now for j equal to I, that expression means that the average of I square is equal to, at the leading order, a squared, but this is exactly the diagonal of this. So this is I average square, plus 1 over d, so I put these 2 together, and this gives me a square minus A square divided by D. Okay. And now I do it. Okay. Now, this, again, what is this saying? So, this is saying that the expectation values of the matrices depend only on the invariance, so only in properties of the eigenvalues of A. It's kind of trivial. I mean, we are doing these averages with the structureless eigenvectors, so we forget about the structure of the eigenvectors after we take the average, okay? But now you have this kind of properties. So, I mean, if you want, let me be a bit pedantic. So, I'm saying that the average of the moment can be written in terms of, so I define the first cumulant is just like the average, and then I define the variance of A, like A square minus A square, okay? And you see that basically at the leading order, so this is equal to K1, this is equal to K1, and then the variance of A enters in the fluctuations of the matrix elements. Okay. Now, I want to tell you that there is a way. So in principle, now with Weingarten calculus, so with the formulas that you can write at every order, you can continue this exercise. Okay, we're not going to do it today. But suppose that for reasons that I left, for some reasons I want to stop at the second order, and now I can write down, let's say, a summary ansatz, or let's say a summary equation which contains all of these. So summary equation. So I write Aij like a delta function of A plus square root of K2 of A divided by D Rij. Where now Rij, okay, let me write it and then explain it as 0 average and variance 1. Okay, so we derived this, and now I want to summarize what I said up to second order in just by rewriting my matrix Aij in the following way. So I'm saying that this matrix, which is there, has a diagonal, which is basically proportional to its expectation value. And then away from the diagonal, it has some oscillating numbers, Rij, which are a random matrix, which has 0 average and variance 1. And all the information is put in, let's say, in front of this with this K2 of A over D. So why this is appropriate? Okay, now this is simple. Basically, when you take the expectation value of this vanishes and you get this. Now if you take the products, okay, I did it properly, so it makes sense, you can check. Okay. Now, this is why I'm saying that this is a toy model for ETH, because you will see that somehow the spirit of when we write down ETH is very similar, has a very similar expression to this, but in this case, this is important. These are real random matrices, okay? And now let me make a point which is very, very important, namely, that somehow we did derive this expression, so this summary equation works only up to second order. So it works only until you take products of two matrices. Right? Because it's constructed in a way to reproduce the expectation value only until you take the products of two matrix elements. It says nothing, in other words, it says nothing about the correlation, higher order correlations of the matrix elements. But not because there are no correlations, just because it's not designed to do it, okay? So, in general, as we were saying, you can continue the exercise. Let me write it here. So, and you will find now, so now imagine you want to do it for the product of n matrix elements, I1. So here I'm taking the product of n matrix elements. And now there are several ways to do this exercise. You can put all the Weingarten formalism inside here and start taking the averages. Okay. Now this is going to be very similar to what we wrote before. Namely, you're going to have an invariant of the matrix A. I'm going to write it Kn of A. And then here some normalization, which is dn minus 1. So this is for n for dn. So this is the, if all the indices are different. Okay, all of them have to be different, not only pairwise. So this, you see immediately, is exactly, is a simple generalization of what we wrote before, right? You see here, for only 1, you get the first, K1, then for 2, you get the variance. These Kn, they're going to be connected correlations at order n. And these, they turn out to be free cumulants. So, right now, you don't know what they are. By tomorrow, you will know. But you have to think just they are a connected correlation function of order n. Exactly as you have the first cumulant, which is the average, the second cumulant, which is the variance. Okay, so this is the first bit, and then as we did before, so another important point here is that if one of the index is repeated, so you see this is AII square, then at the leading order in one of Verdi, there is a factorization. Okay, so this is AII square at the leading order is equal to the average of AII squared. So now you kind of generalize this. So you have that A, I1, I2. And now the kth index, I repeat it. So K minus 1, I1, A, I1, IK plus 1, IN, A1. So the nth index, the kth index now is equal to the first. So this at the leading order in D factorizes. So it's equal to A1, A2, AK minus 1, A1. Plus correction, which are D to the minus 1. Okay. Okay. So why I'm making this point is because the same is going to be true also when we talk about eigenstates of chaotic Hamiltonians. So this is an excellent summary equation until we talk about products of two matrix elements. But thanks to Weingarten calculus, one can go beyond and compute products of many matrix elements. And actually, this calculation can be done also with the Hitchkinson-Zuber integral. There are many ways to get the result. Okay? Good. I think this is a good moment to take the pause, and what we are going to do later is now to elevate this from structureless random matrices to chaotic Hamiltonians. Okay, we can take the break. Okay. Let's start. Okay. So let me make a point which was triggered by your questions that I wanted to postpone, but just to be more clear. So there is, let's say, a diagrammatic interpretation or another summary, the pictorial summary that you can have in your mind for what we just said. So you can imagine to represent your matrix Aij like a vertex joining two indices I and j, okay? And so what we're saying, okay, let me write this with I, that the only expectation values are those, let's say, where there are closed loops, okay? So where II average corresponds to a simple loop with only one index, okay? This is simple to read. You have I, and then you have the matrix, which goes back to I, so this is AII averaged. Now here, this is AII square, so you can imagine you have two indices, but then you're identifying two of them, so you draw a line which connects these two indices. This is dashed in blue. I don't know if you see it, okay? And now what this is saying is that at the leading order, this object, let's say, factorizes in terms of one loop squared, okay? This is a pictorial way to do this. That you can imagine you're cutting along this edge, and so you obtain two simple loops with one index. Now here you have Aij, Aji, so you have a simple loop with two indices, I and j. Okay. And now what we did above later is just to generalize. Now you have a simple loop with n indices. They're different, so you're not drawing any line connecting them. And then here, maybe I was not clear enough. Here what we said is that the kth index is equal to the first one. So here there is A1, and then the IK is equal to A1. Okay? So there is this dashed, this is clearly blue, dashed line between the two, and so this at the leading order factorizes in terms of two loops. Okay. Now, another point that I want to make is that we made this derivation at, yes? Yes, precisely. Perfect, exactly, yeah, exactly. Okay. Then what else did I want to say? That you can do this exactly the same calculation for the orthogonal ensemble. So in this case, we use Weingarten calculus, which is exact at every d in the case of unitary matrices, but you can clearly do also for orthogonal vectors. And the only difference in this calculation is that you would obtain a factor 2 here, okay, and not 1. So, okay, I'm saying this for you is a mystery, but it's like this, okay? And but you see at the leading order, let's say these properties are the same. So this still factorizes, I mean, this is just a factor 2 here. But it is related to the fact that the variance of orthogonal random matrices is of diagonal is 1/2 than the one of the diagonal, which is one of the exercises. Okay. Okay. Now this is to conclude what we were discussing before. And now let's move to the cool part, which is the one of considering now real Hamiltonian systems and not anymore this kind of toy models or random matrices. And the kind of approach that I'm going to take is complementary to the one of the previous lecture by John Chocker, which is to include still this kind of minimal model of physics, but not in terms of locality, but in terms of energy conservation. Okay. So I kind of want to see, or we want to discuss how this picture is modified if H now is a many-body Hamiltonian, okay, which is conserved. Now, the first thing the first kind of result that is important to know is kind of an historical one, and we're not going to spend many time on it, which is known as the Berry conjecture. So you see this name comes back and back and back again in 1977, which was based again in this kind of semi-classical limit. And now the statement in that case, so this kind of semi-classical limit where one has an Hamiltonian in terms of conjugate variables that actually comes from the quantization of a classical Hamiltonian, blah, blah, blah. Okay, and now the statement he made is that he conjectures that the individual eigenstates at sufficiently high energy are such that, so individual eigenstates, they look like Gaussian random vectors. So here, they're Gaussian random vectors in the component Q. Okay. So these are Gaussian. And yes. So here, fix the basis, which is the basis, let's say, of you can think about a billiard or some phase space. Now, the statement is that the kind of topology or of the distribution of the overlaps of your eigenstate with the coordinates is going to be very different in the case in which you have a regular or a chaotic eigenstates, and that eigenstates are going to be, let's say, Gaussian vectors, Gaussian random vectors. So I already told you that I don't really want Gaussian, I want unitary random vectors. But what's important here in this case is that they look Gaussian random vectors in a small energy width. So this kind of was a very crucial intuition, and the eigenstate thermalization hypothesis, I would say it's can be seen as a many-body version of the Berry conjecture, but now applied not by looking at the individual statistical properties of the eigenstates, rather really looking at the matrix elements. Okay. So now, besides the classical limit, now let's think really about this kind of many-body Hamiltonian, in which we said again, we have n degrees of freedom, and d, the dimension of your Hilbert space, is exponential in n. Okay, and now a very important quantity is the density of states, which we called the level density in the case of random matrices, but okay, here we're, so this counts the number of states at a given energy. So how does the many-body spectrum look like? So let's put here the ground state is 0. Now, the eigenvalues of chaotic Hamiltonians, they're ordered, right? So you have E0 smaller than E1. Okay, so you have your ground state, then you're going to have, okay, maybe some few excited states that you can treat with as quasi-particles. Okay, let's suppose finite system, so you have the same. And then as you go to higher energies, you're going to get many more eigenstates. So and if your model is very large, this looks, let's say, like a continuum. And so if you look at your density of states, oh, sorry, this plot is terrible. So you have that the bulk of your spectrum is, so most of your eigenstates are really in the bulk of the spectrum. Okay, so this is a D of E. But then if you look at a fixed energy density, so again, you remember I was representing it like this, so I want to consider a fixed energy density, so actually let me write it E equal to E over N. So if I look at a fixed energy density and I resolve in a small interval here, okay, this which looks a continuum from a distance, here you're going actually to have many eigenstates whose level spacing, whose distance is on average the inverse of the level density. So this is exponentially small with the system size. Why? Because, okay, sorry, I didn't say this. This level, this density of states, okay, so we can write it as E to the S of E. So this is the thermodynamic entropy. So these are definitions in standard thermodynamics. No? So I'm just saying that the thermodynamic entropy is the log of the density of states, and then there is some inessential energy normalization. So what I'm saying is that the density of states is exponentially large with the number. So this is the thermodynamic entropy, so the entropy is extensive. Okay, so the density of states is itself extensive. So the inverse of the density of states, which is telling you how much the eigenvalues are close at a fixed energy density, is exponentially small in the system size. Okay. Now, why are we making a big fuss on this kind of structure? Is because, very importantly, now that we're treating, let's say, many body Hamiltonians, we don't have an ensemble. We are thinking about a fixed Hamiltonian in principle. Yes. So the eigenvalues I'm discussing, they're not really random. The eigenvectors, they're not random eigenvectors anymore. I do not have an ensemble in principle over which I'm averaging on. Okay, it is a bit like we were saying before, or like John Chucker said, we don't want to solve the full problem, let's say. So even if the eigenvalues and the eigenvectors are non-random, I still have that at a given energy density, the specific arrangements of my eigenvalues and eigenvectors is irrelevant. In other words, I have, let's say, a separation of scales. So if you wish, your energy density, which is the physical scale, the physical energy scale of your initial state of the object you're looking at, is much bigger than the level spacing. Okay. So in general, you have that the mesoscopic properties at a given energy. Okay, so do not depend on the microscopic arrangement. What does it mean? It means that independently of the specific structure here, the properties at E should not depend on it. So I can imagine I can average over these small energy windows. So basically there is an invariance of, so I want to invoke a sort of invariance of mesoscopic properties on the microscopic arrangement of the energy spectrum. Okay. And this somehow defines the ensemble I'm talking about, we want to talk about. So we have a given Hamiltonian, we can put it on our computer, the energy eigenvalues and eigenvectors are fixed, so it's not random. At the same time, the properties on the mesoscopic scale do not depend on the individual arrangements. Okay. So the eigenvalues and eigenvectors behave as pseudo-random. Such that I can still talk about statistical properties now. So you could have done this question even before, like what do you mean about the statistical properties of eigenvalues and eigenvectors? So now the spectrum, so my EI and my eigenvectors are going to behave as pseudo-random matrices with this idea that there is this separation of time scale. In other words, okay. So this is the first, I see confused faces, but it's normal. So I want to invoke a sort of invariance under small rotations, so under reshuffling of few eigenstates. Do you have questions? Really see. It's too confusing what I'm saying. Mm-hmm. Yes, I mean some property, for instance, at a given energy density. So this is order 1, okay? Because the energy is extensive, so this is order 1, and this is exponentially small in n. Okay, so this is much bigger than this. So you can do averages over small energy shells. Yes. Now, what is really important for what I want to say is that somehow this kind of pseudo-random structure, which does depend in energy. So I do not want to throw away my energy dependence. Or the game now is going to include the energy dependence on this sort of randomness. All this energy dependence, it's coming with me. And it means that now my matrix elements will not look anymore as a structureless random matrix, but it will have some structure, yet with fluctuations. So my kind of now, the main, the protagonist of the rest of the course is going to be Aij, which now is the matrix element of observables in the energy eigenbasis. And yesterday, in the first hour, we argued why this is important for dynamics. But now this is not going to look anymore like this, but this will have, let's say, some structure in energy. So this is also something that you can do. You can put the matrix on your computer, and you will see. So here, what I want to represent with this ugly picture is that if you take now matrix elements which are on the diagonal or close to the diagonal, their expectation value is larger than if you have matrix elements which are very far from the diagonal. So if the energies are very different and you have a many-body physical system, this matrix element should be small. What it means is now, so what I want to say is that if you have two energies which are very different, and now you're computing the expectation value with a local operator, you cannot connect matrix element, you cannot connect eigenvectors which are very different in energy. So this has to be small. So this kind of, the fact that there is a structure in energy has to be reflected in the matrix elements, okay? Well, I mean, in principle, you can imagine that if you have a super complicated non-local observable, you can connect to energy eigenstates which are very different in energy, no? Yes. I'm going to make this statement more precise in 1 second. It was just to give you a qualitative way. But now, what I want to point out, so which kind of invariance are we going to invoke now? Is that here, so suppose now I take an Aij here, okay? So this is my I and this is my J. Oh, let me redo the plot here. So with this dot, I indicate the signs. Oscillating signs is not very clear. Now I take a matrix element, Aij at a given I and J. And now I have basically, okay, rows and columns. So let me write it here. Here, if you zoom around a small interval, we said that you're going to have many eigenvectors here in a small energy interval. And also here, you're going to have exponentially many of them. But what we want to study are somehow only mesoscopic properties. So you can imagine that you can locally, you can average over the small windows of each individual eigenvalues. Okay, so you can imagine that here, what you're doing a small rotation, that is a small u. So what I want to say is that the mesoscopic properties of my matrix are going to be invariant under small rotation. So small in energy, okay? So let's say I define A of U, which is U, A, U dagger, where now my U, it's not anymore a full unitary matrix. There are small unitaries that act only locally in energy. And this is the concept, let's say, of local rotational invariance. That is at the basis of what discussed by Berry, Deutz, and others, but in this kind of form is Foini-Gurchan. Okay. So this is precisely the same property that allowed us to derive our toy model. So now you have to think about these are small unitaries on a small energy shell. Okay. Now that we are invoking this, it's clear that what I want to do is that I want to take the toy model we wrote before, and I kind of want to introduce energy dependencies. So now, let's say again, the summary. Let me write it like we did. Now we have that AII on average is going to be given by a smooth function of the energy EI. Or let me write there here. Okay. I have that AII square on average is going to factorize. So this is AII average square plus order d of e to the -1. And then I have that AIJ, AJI on average is going to be given by a smooth function okay. So where now I'm including the energy dependency. So if I have EI and EJ, I can define some average energy, E plus, which is EI plus EJ over 2. So this is the average energy between these two eigenstates, and I can read the average energy on the diagonal of this matrix, for instance. So its average energy would be here, E plus, and this also I indicate with the small e plus its density. And then I have the energy differences, or the frequencies, EI minus EJ. Okay. So yeah, just 1 second. So what I want to say is that now I want to keep, let's say, the dependencies of frequency and energy. So you see, now I'm invoking some smooth function. Here, this A of E and F of E omega are smooth functions of the arguments. Okay. Where all the physics is encoded here. So for instance, going back to the question that was asked, now this function depends on the energy difference. And what I wanted to say is that if the energies are very different, this should be small. And now I'm putting all this information here. So this function f is going to decay for large energy differences, so it's going to decay at large omega. So I'm putting all the information about the physics in this function here. Yes, there was a question. Yes, we assume that in general. Otherwise, what would happen? Yes, okay. But also you would have no dynamics. No? So our original motivation, okay, this is worth repeating, is that we want to describe things which have a non-trivial dynamics. So, and clearly if they commute, nothing happens. Summary, yes. That's an excellent question. So your colleague is asking, okay, so what I'm saying is that here there is a delta, so this U is defined on delta times delta, okay? And you see from here, this delta should be much larger than the level spacing because you want sufficiently enough eigenstates, but should be much smaller than the mesoscopic, okay? Now, the precise scaling with the system size is not known. So one could say that should be much larger than e to the minus n and much smaller than n, smaller than 1 over n, but the precise scaling is not known. So at this level, it's a bit. Yeah. Mm-hmm. Mm-hmm. I mean, if you have very strong disorder, you have localization, and so all this picture is spoiled. Because you cannot anymore invoke the fact that your eigenvalues and eigenvectors should look like random matrices. In that case, you should think about independent random variables, which is very different. But going back to this other question, how big should be delta, this is a bit similar to the question, how small should be h bar? So you want to go in a limit where you have sufficiently many values, eigenvalues over which you're averaging on, but it has to be much smaller than all the physical scales. That's a good question. So I would rather say it's the opposite way around. So let's say you need fewer, you need to average over fewer elements if you're looking at smaller cumulants, but I'm not 100% sure this is correct, so maybe I can think about it more and tell you. It's quasi-orthogonal. So that the matrix element between two Hamiltonians, this is what you want to do? No, sorry, can you repeat? I mean, I don't know how to treat this, but I know to write how to write this expectation. I mean, maybe this is connected. How big should be delta? And this kind of argument is very hand-wavy, and I don't know how to write it mathematically in a more precise way. But I think it's a very good question how to do it in a more precise way. But I don't know how to do it, so I know only about how to treat this. Okay. Now, you remember now what we had in our toy model. Let me write it in green. We had here A, then here we had A square, and here we had K2 over D, no? This was in our toy model. And here everything was flat. So flat in omega and in energy. It was just a constant for all the eigenvectors, which precisely means it's structureless. Eigenvectors do not matter. Now the eigenvectors matter, the order, so these functions are going to be dependent on energies and frequencies. Okay. Now let me just create a summary of this equation, but you know already how to do it, so now I can summarize my ansatz in the following way. Oh, sorry. Okay? And this is what you usually find when, 1 second. So this is the Eigenstate Thermalization Hypothesis. And it's due to Strelnitsky, 98, written in this form, yes. They're the same. When you say they're close, the question becomes about the limit of omega going to 0. Okay. Okay. So this is what you usually find exactly when you open the review or when ETH is stated. Okay. But so the point I wanted to make is that this can be thought as a summary ansatz for the first products of, let's say, for the expectation value of Aij and products of two matrix elements. But here, nowhere, I'm saying that there are no correlations. Okay, this is just a summary ansatz. But now, why in this case we're talking about hypothesis and not, yes? What is there? No, it's taken before. And this should be 2 in the case of orthogonal, the class of orthogonal. Yes. Precisely. So we're going to do this tomorrow. So now, in these 15 minutes that they are left to us, we're going to see why, let's say, we like this energy dependency, because all physics, equilibrium physics and non-equilibrium physics at the level of 1 and 2 point function is encoded in these smooth functions here. Okay. But this is okay only up to 2 point functions. So if you want to go to multi-time functions, you cannot use this summary ETH ansatz. You need more, and we're going to do that tomorrow. Okay, other questions while? Okay. So now, as an exercise, and I really invite you to do it, let's say you should show that these ansatz here, either in this way or this way, is enough to show thermalization. Okay, so you remember yesterday we started from the quench experiment, and then there are 2 things that you can compute, the diagonal average and let's say the fluctuations, and then using this you can show both that the diagonal ensemble for states like we discussed yesterday goes to this smooth function, which you can think about the microcanonical distribution. Okay. And then that fluctuations are small. So this is important that you do it for consistency. And it's not too complicated. Now, what I want to discuss now are, let's say, equilibrium expectation values. Okay, I know that you're tired because today is 4 hours and lunch is only 15 minutes far, but this is simple, so you can be focused. Okay, so now what I want to use, I want to, let's say, compute the thermal expectation value. So this is e to the minus the canonical expectation value, A. So I'm going to do this because this is the basis for every ETH calculation that you will ever need. So there are the crucial steps. So here what you do, you rewrite everything in the energy eigenbasis. So this means that here you have e to the minus beta ei over z, aii. Okay, this is what you're doing. And now you use ETH. So you substitute the individual expectation values with its average. And why can you do it? Well, you do it because basically you're summing over many of them, so you expect that the summation will wash away fluctuations. So this becomes sum over I of e to the minus beta ei over z. and then here you put the smooth function of ei over n. And then you pass from discrete sums to smooth integrals. So sum over I, you substitute it with the integral over the energy of the density of states, d of e. Okay. But now I want directly to rewrite it as e to the s, which is what we wrote above. That's the definition of the density of states, okay? So this, you use it extensively when you do kind of ETH calculations. So this integral becomes, this sum becomes the integral of e to the s of e minus beta e over z I microcanonical of e. Okay. And now, this kind of integral is not too unfamiliar to statistical physicists, no? Because you remember, we're saying that energies and the entropy, they're both extensive. So let me be very, very, so here you represent so you can say that this is the integral over e to the n, and then you have s of e minus beta e, a microcanonical of e, okay, divided by z. Okay, so there is an n factor, and you want to solve this integral in the thermodynamic limit. So what do you do? Yes, you do saddle point, no? Okay, so when you do saddle point, basically you have that because this function depends on n only smoothly, so it's a so basically you have that this is given by the saddle, and the saddle of that is determined, let's say, let me write it here, by when the derivative of the entropy to respect to the energy is equal to beta. So this, let's say, defines my saddle point, no? E star. But this is precisely the thermal energy, no, that you do in StatMech. So then, basically, the numerator and the denominator at the saddle points simplify. So you have that this is equal to the microcanonical function at the thermal energy density plus correction, which are 1 over n. Okay. This correction is 1 over n. You do it by saddle point, okay? And now if you use the ETH on the single matrix element, you can imagine that this is basically saying that the thermal average is the same as the one that you would obtain for a single eigenstate. So this is when you hear single eigenstates in quantum mechanics contain all the statistical mechanics. This is what you mean. Because, okay. Now this is 1-point function. Good. And now we want to do 2-point functions. So clearly, we cannot do all of it, so you will have to do some of it on your own. In particular, I want to study the connected correlation function. So let me start the exercise, and then you will finish it. So here, I want to compute this object, and I want to repeat the steps that I started before. So the first step is to write everything in the energy eigenbasis. So here you have the trace, so here minus beta ei over z, and then you put 2 resolutions of the identities. So one is to take the trace, okay, which is I, and then you put 1 here, which is sum over j. Okay, so here you get aij square e to the I ei minus ej t minus. Okay, so now you immediately see why we have been arguing that, let's say, 2-point functions, so that we need product of two matrix elements to describe two-point functions, because these are the ones that enter in this. Okay. So it's clear how I pass from this to this. Okay. And now what you do, since you want to use these ansatz, and you see these ansatz is formulated in two different ways, if the indices repeat or if the indices are different. So what you do is that you separate this summation in a contribution where the indices are the same and a contribution where the indices are different. So basically, this is equal to the sum over I different from j let me write omega ij, so here I put the energy difference. And then you have sum over I, aii square, e to the minus beta, I over z, minus a beta square. Okay, so this is also very complicated manipulation. But now, so what this is another exercise that you should do is that exactly following the same step. So you do another saddle point integral, basically, and you show that at the leading order, this object factorizes. So because you can repeat, so you see here I have aii squared. In 1 over d, I can substitute my ETH ansatz, so this becomes a microcanonical of EI square, and then you solve it by saddle point, and at the end you're going to obtain the square of the microcanonical at the thermal energy, which is exactly equal to the leading order. So this gives you something which is order 1 over n. Okay. Now 1 over n is different than 1 over d, because here d is exponentially large in n. So this is kind of a small correction, but it's only 1 over n, so it's not exponentially small. Okay. But now we are left with this. Okay. And so what we want to do now is to rewrite this in terms of that smooth function. So maybe I should not do it, because I see from your faces that enough is enough, but this, okay, calculation is going to, in the Lagrange limit, this is equal to the Fourier transform of the smooth function at the, okay, let me write it and then I comment. Okay, so. Okay, let me, okay. So what I obtain by using ETH, okay, is that two-point connected correlation function can be written as the Fourier transform of the smooth function appearing in ETH. Now the calculation is not difficult. Maybe I can start, I mean, if some of you is interested, you can try to do the exercise, or if you don't manage, you can come to my office this afternoon and we do it. But what is important is, why do we have those functions there? Because those, they give us how two-point correlation function go to 0, or how do they evolve, a two-point connected correlation function. And I remember this morning there was one of the questions, how random matrix fails in describing what happens in, let's say, physical systems. Well, it fails here, for instance. If you put the random matrix result, that does not depend on frequency, you know, if you put this. If you take this and you put it here, you take the Fourier transform of a constant that's just a delta function. So you get no time-dependent two-point functions with random matrices. Instead, here, I'm saying that, okay, there will be a function which is left undetermined that dictates how two-point function will change in time. Okay. Okay, there are questions. What do we eat for lunch? Okay, then maybe we can conclude, and then tomorrow we will recap all of this and go ahead.